Welcome to Lesson 4C, Tank Filling. We're going to look at tank filling and how to estimate vapor emissions from filling a tank. So let's look at the setup here. We're filling a tank with some liquid VOC. And so the liquid is coming in, and inside the tank, let's suppose we already have some liquid and it's evaporating since it's a volatile substance. And then this CJ, there's a partial pressure, and you can convert that to a mass concentration. And we'll assume well mixed. So anywhere you take this reading, you measure the CJ, it's the same. So we'll assume well mixed conditions inside this tank. Now the key is, as this liquid is poured in, the surface of this liquid will rise with time since you're adding more liquid. And then the surface of that liquid acts like a piston that pushes the air up. And so imagine placing this liquid with a liquid piston that's moving up. And so what happens is the air and the vapors have to go out. So there's a Q air, there's a volume flow rate of air plus VOC vapors that is coming out. And then as you keep adding liquid, it's going to push more and more of that air out. If you fill the tank up, all of the bulk air, which again contains both air and VOC vapors, is going to come out. So you will release some VOC into the atmosphere. And these will be vapors since it starts as a liquid, but because of evaporation, this is now vapors. And so m dot J is how much mass you're releasing per unit time. It's the source strength or the mass flow rate of the contaminant. Remember, we use the J subscript. So CJ times Q of the bulk air. So the total volume flow rate of the air. And we can also call this SJ, which is the same as m dot J. So this is our equation for the rate of emissions coming out of the tank. We call this effect of the piston the displacement effect, because it's acting like a piston that's pushing, it's displacing the air with the liquid and therefore pushing the air out. There's nowhere else for that air to go. If you had this closed off up here, if you had this sealed, you'd be adding the liquid, you'd have to be building up pressure in here continually in order to get that air to do something. The air would just compress. But here we have it open so the air comes out. Okay, so that's the basic physics of what's going on here. So now let's do a conservation of mass. And we'll do this first for the bulk air. So Q bulk air coming out must equal Q of the liquid coming in. How do we know that? Well, again, this is all incompressible fluid mechanics. So as we add the liquid, whatever the volume flow rate of the liquid coming in, since nothing's compressing, the same volume flow rate of air, bulk air, must come out. That's straightforward. And then we have the mass concentration of the contaminant. So CJ is by definition MJ, little mj, over volume of the bulk air. And remember, going back to the first week, this MJ is NJ times capital MJ over, again, V of the bulk air. We're going to deal with only ideal gases in this course, so the VOC and the air are both ideal gases. This is an ideal gas mixture, and PJ of the species, the partial pressure, times the volume of the bulk air is equal to NJ RUT. That was one of our forms of the ideal gas law for the species. And then you combine these together to get CJ is equal to capital MJ PJ over RUT. So we have an expression for CJ as a function of PJ. And finally then, m dot J, or S, capital SJ, is, as I said above, CJQ of the bulk air. So we can write then m dot J is equal to, and putting this into that equation, capital MJ PJ over RUT times Q liquid in. And that's our, not final, but that's one final equation that we get from this to give us everything we need to figure out what m dot J is, or the source strength, due to evaporation when you're filling a tank. So this is the displaced vapor that comes out. The only thing we don't know is PJ. So that's where we use something that we learned previously. If you have a tank filled with a little bit of VOC, so let's draw this again with just a little bit on the bottom there, a little bit of liquid, but it's been sitting there for a long time. So a good example is your gas tank in your car. So it's been sitting there for a couple days, you haven't used it, and it's closed off at the top, but there's a little bit of gas, it's almost empty. So what is the pressure, PJ, the partial pressure? Well, as we learned before, when you have been sitting there for a long time, PJ is equal to PVJ, the vapor pressure. once it reaches that, there's no more evaporation since the air is saturated with the VOC vapors. So if that's the case, if we know it's been sitting there for a long time, if you're doing a homework problem or a quiz question and you see the words for a long time, that's your key to know that this has been sitting around long enough for PJ to equal PVJ. If you just poured this stuff in, PJ will have to start from 0 and it will work itself up to PVJ, but that'll take some time depending on how fast the VOC evaporates. So since we have PJ equal PVJ, it's the vapor pressure, then I can ask how much of the vapor in the tank comes out. So the question is, how much of the VOC vapor is emitted into the air if we fill up the tank with liquid VOC like we're showing here? How much comes out the top there? And the answer is all of it. Because if you fill up the tank, you have displaced all of the bulk air that was in the tank, which is at this partial pressure. Therefore, all of it comes out, and that gives us a way that we can calculate the total mass flow rate or the total mass. So here's in terms of the flow rate. We can also write that in terms of mass instead. And so this applies to, for example, if you drive up to a gas station and you start filling your gas tank. And I just did that this morning on my way in, by the way. And so I had a little bit of gas left and filled up the tank till it stopped. And so I filled it up completely. And all of that vapor that was emitted as air pollution of the VOC vapors into the atmosphere. That's why you smell it, by the way. When you get gas, you can smell the VOC, in this case, the hydrocarbon fuel, gasoline vapors coming out. You can smell that when you're filling up your tank. And there's really no way around that unless you have a vapor recovery system, which we'll talk about in a minute. So let's do an example of filling your car's gasoline tank. You need gasoline in your car. Tank is nearly empty. There's a little bit at the bottom, otherwise you wouldn't be able to drive to the gas station. The tank volume is 15 gallons, which is like my car. Estimate to 2 digits is good enough. The mass of gasoline vapors emitted into the atmosphere during a fill-up. So let's first look up the molecular weight and vapor pressure of gasoline. These are kind of all over the board because there's different brands of gas and different octane ratings and all that, but these are some pretty typical values. Molecular weight given here, 110 kilogram per kilomole, and PVJ, the vapor pressure, is given in both units of millimeters mercury and kPa. And the equation I gave you this top one, which is for a rate. This one's in terms of the rate of mass emitted, and this one is in terms of the actual mass emitted. So instead of Q, we use V, the volume. So if I have a tank that's 15 gallons of volume and I add 15 gallons of liquid, I have 15 gallons initially, roughly, of bulk air, and all of that comes out. So we know if it's been sitting there for a while, the partial pressure of the gasoline is equal to the vapor pressure of the gasoline. The key then is to set PJ equal PVJ, and then we'll plug into this one since we're worried about total mass. We don't care how fast we fill the tank. We just want to know how much mass has gone out in the atmosphere. And I did all this for you. This is the vapor pressure, the 22.5 kPa. That's my PVJ that I have up there. And we have our MJ here, and I plugged in my 15 gallons as my total volume. RU, temperature, we're assuming it's SATP. And then all these unit conversions, especially meter cubed to gallons is a useful one sometimes. And to 2 digits, I get 0.057 kilograms. So we estimated that approximately 0.057 kilogram of gasoline vapors into the atmosphere for a 15-gallon fill-up of gasoline. That doesn't seem like a lot, but it adds up if you have to do this every time you get gas and every time the millions and millions of other people gas up their car. There's a lot of gasoline vapor that comes out from gas stations. You can kind of smell it when you drive there, even from all the other people's cars, typically, unless it's a really windy day. Let me take this chance to comment about bias in the media. I've mentioned this before, but this is kind of interesting to think about. I want you to watch for bias when you're reading articles, and it could be any article, not just in this class, you're reading about air pollution or global warming or something, but no matter what you read, people tend to be biased and they try to spin things to what they want to get across. So here's 4 different ways to write this statement that I have up here, which is my result. Okay, you emit only 0.057 kilogram of gasoline vapors into the atmosphere. Well, that's someone who wants to make it look small. You can say the same thing. You emit 57 grams of gasoline. The rest of it's the same. So you're a little bit biased toward making it look like a lot. You leave out the word only and you change it to grams instead of kilograms. Or you can say you emit 57,000 milligrams of gasoline. And these are all identical statements technically, but 57,000, if someone sees that, and if you're not scientifically oriented, you might think, boy, that's a lot. Or if you really want to try to convince people that this is really bad, you say you pollute and contaminate the air that we all have to breathe by emitting 57,000 milligrams of toxic and odorous gasoline vapors into the atmosphere each and every time you fill up your car. This would be someone really biased and worried about the air pollution that we put out with the car. So how much does this actually cost? How much does this cost in dollars per fill up? So I've been teaching this course since 2014 every spring, and every year I keep track of the average cost of gas. So you can see it was in 2014, it was pretty expensive, $3.50 a gallon. It went down to $2.50, $2 in 2016, and then it kept fluctuating around there ever since. Here's a revised table with more recent data. From the above, we calculated this 0.057 kilograms. Gasoline costs $2.80 a gallon. I looked up the specific gravity of gas and liquid gasoline, and it's about 0.75. Gasoline is lighter than water. This is the ratio of gasoline density to water density. That's what specific gravity is. And then the density of the gasoline is therefore Sg of the gasoline times rho of water. So that's equal to 750 kilogram per meter cubed. And here's the conversion that we had seen before. So now we can calculate the money, and I'm going to do that in cents wasted. That's basically lost as vapor into the atmosphere each time we fill up our tank with 15 gallons of gasoline. Here's the equation that I came up with. I put the cost per gallon first in dollars, and then I know that I have emitted 0.057 kilograms, so those have to go in the numerator. And then I know that I have a density of gasoline, so it goes in the denominator, so I can get rid of kilograms. And then I convert from meter cubed to gallons, and I can get rid of the meter cubes and the gallons, and then I'm left with just dollars, and I change that to cents. So these are just unit conversions, and I come up with about 5.6 cents per gallon. That's not very much, but again, if you add this up over all the people filling up their cars every day, millions of people, it can add up to a lot of money. And all this is just wasted. It's into the air. So let me make a statement here. This is wasting money and it's emitting air pollution. And it's not possible to eliminate this waste because of the displacement effect. As you put your gasoline liquid into your tank, the vapors that are there, this stuff is already evaporated in your tank. It's got to come out. It's got to come out of your tank. There's no way to avoid that. The only way to eliminate this waste and this air pollution is to have some kind of what we call a vapor recovery system, which will capture some of that vapor before it goes out into the atmosphere and then recover it. This is what something like that looks like. Around here in State College, we don't have these kind of gas tanks. If you look at the nozzle, it's just a solid cylinder. But if you look closely at this one, I took this near Pittsburgh when I was visiting one time, and you can see that there's these holes here. So what's going on here? There's also this rubber cap that fits real snug over your opening for the gas to go in. And so here's your nozzle and the trigger and all that. And how this works is it's actually a tube within a tube. And let me draw this for you, and then I'll talk about it. So here's how this works. This nozzle with these holes is actually a double cylinder. So there's two cylinders, two pipes basically, an inner one and an outer one. And so it's a tube within a tube. And the liquid gasoline comes in from the tank at the gas station, and the liquid comes and flows into your tank and starts filling up the tank. And meanwhile, the air and the vapors, I'll use blue for that, comes out. So this is PVJ, PJ equal PVJ in here. And those vapors plus the bulk air come out, and those go in through these holes, and then those go out here. And so these are the vapors coming out. It's important that you have a tight seal. If you've ever used this at a gas station, you have to put it on nice and straight and make a seal so that this works. Otherwise, the air is just going to escape and bypass that rubber booty and not do it well. This goes to a vapor recovery system. Typically, what they do is they cool the vapors really low temperature and condense it back into liquid, and then they put it back into the tank in the gas station. It's kind of expensive, but it does work to keep the gasoline vapors from going into the atmosphere. So other than some kind of sophisticated vapor recovery system, is there any other way to avoid these emissions? So what we'll do is define a filling factor, defined as the actual partial pressure PJ over the maximum possible partial pressure, which is PVJ, and F has to be between 0 and 1, because the maximum PJ is PVJ and the minimum PJ is 0. So when is it 0? F approaches 0 if you have an empty tank completely empty, so there's no vapors in there to begin with. So you have an empty tank at T=0 when you start filling, and you have a very slowly evaporating VOC. Well, that's kind of an oxymoron, because if it's slowly evaporating, it's not a VOC. So they'll just say it's slowly evaporating, and then your F could be like 0.1 or 0.2 if you fill up this tank pretty fast and you don't splash and stuff like that. You might be able to get away with that. It's 1 if the tank was partially filled and has been sitting around for a long time, like I said. This F is kind of like a relative humidity, but with some species of VOC rather than water. Here's the point then: if any amount of the VOC has been sitting at the bottom of the tank for a long time, partial pressure will equal the vapor pressure, and then F is 1, and there's really nothing you can do about that. You already have evaporated all the VOC into vapor that you're going to, and it's going to have to come out. So unless you have a vapor recovery system, that is going to go into the atmosphere. So the source strength, or the m.j, is here. The only difference between this and the previous equation is we threw that F in there. It's just a fudge factor. Instead of Pj, we put F times PVJ, since Pj is equal to F times PVJ from this equation. So this is the more general equation that we'll use for these kind of problems. The thing that remains then is to figure out what F is. So we already said F is 1 if you have it like the gasoline filling up tank, like I told you in that previous example. But F will depend on a number of things. And we're talking about the case of an empty tank initially. So it's an initially empty tank. There's no vapor in that tank to begin with, and then you start pouring the liquid in. So F depends on how fast the VOC evaporates and how fast the tank is filled and how you fill the tank. And these will give you some F that's in between 0 and 1. Now here's some quick and dirty examples for different kinds of filling. Splash filling, which is how you fill your gas tank in your car. You just have a nozzle that comes in and the yellowish color liquid coming in, and then the vapors go out and it's splashing around. There's a lot of evaporation because of all these little drops and stuff. So there's a lot of evaporation going on while you're filling this up. We're talking about filling up initially empty tanks. So it's evaporating as it's pouring in. There's some evaporation coming from anywhere the liquid is exposed to the air. And then that all has to go out. So splash filling, if it's a very volatile liquid, PJ is approximately PVJ because you have all this splashing going on. So F is approximately 1. It might be 0.95 or something like that. Now, you might save some by doing submerged filling. So if you have your pipe coming in, instead of just splashing it from the top, you have a pipe that extends to the bottom, and then at first it's splashing, but once this level reaches the lip there, you don't have any splashing anymore, and this just rises nicely like a piston. So there's some evaporation going on, but again, depending on how fast it's evaporating, this PJ will be less than PVJ because it hasn't had a chance to fully evaporate and saturate. So F is, it might be approximately 0.5. Or you can do a similar thing that's called bottom filling. So this was called submerged filling. Bottom filling is the same kind of thing where you're putting it in from the bottom. Now it goes into a baffle and just spreads out. And so once it reaches past this level, it's basically just liquid that's moving up like a piston and slowly evaporating. And so again, PJ is less than PVJ and F is typically around a half or so. So this comes from a handbook on air pollution control. So that's one way to do this a little bit better, but the only way you can totally eliminate these vapors going into the air is to have a vapor recovery system like we talked about. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.